Thank you everybody for attending. It's a particular pleasure to introduce today's speaker, Professor José Andrade from Caltech. José is the George Hausner Professor at Caltech, and equally importantly, he was a member of the faculty here at Northwestern. So we are especially happy to have him back. It's a sort of homecoming for him. So for everybody who's working on mechanics, as many of us do, Professor Andrade doesn't really need any introduction, but I feel compelled to give a brief one. So José's work focuses on computational geomechanics, and he has given seminal contributions to the analysis of granular and porous materials under fluid saturated conditions, and in particular to particulate materials and granular materials in general, the methods, the techniques that he has developed for analyzing granular materials with variable shapes, complex shapes, and the interaction between these particles are rapidly becoming a standard. And I could go on and on the many awards and recognitions that he got, but José is not only an outstanding scholar, but he's an inspiring speaker. And so I don't want to steal any more minutes from his talk. So thank you so much, José, for joining us today. And feel free to start anytime you're ready.
Thank you very much, Giuseppe, for that very kind introduction. Good morning, everybody. It's 9 o'clock, a little past 9 o'clock here in California. It's great to see many old friends and new friends. It's, as Giuseppe said, it's a bit of a homecoming for me to visit Northwestern. Okay, this is what we've got right now at this time. But through the magic of the internet, I'm very pleased to be here with you and share with you some of the work we do in the Cosimo lab, the Complex Systems lab. And the work I'm going to show you actually has very clear and strong ties to Northwestern, not only in the present, but also at the inception of this work. Many of the ideas that I'm going to show you today were born at Northwestern, and I'm going to make a point along the way of where those ideas come from. But I think you're also going to recognize it because it's pretty obvious where it comes from. I hope you can see my pointer. I'm going to be using this pointer to point, and so that looks good. I want to acknowledge also many of our collaborators, and I'm going to do that along the way, but in particular, 3 PhD students, my former PhD student, Kostas Karapiperis, who's now at ETH Zurich. He did a lot of the data-driven work that I'm going to be showing you. John Harmon is a current PhD student in my group. The breakage work that I'm going to show you is partly done by John Harmon. And then a lot of the work of Rigoberto Moncada on sea ice modeling. Let us get started. We're starting a little late, and I apologize for that. This is a current group. Today, we are a little larger than 10 people. We ebb and flow between 10 and 12 people any given time, and number of postdocs, and Jenny Campbell, who literally runs the group. I wouldn't be here without Jenny. And so we're a happy bunch, and we have fun together. And the work I'm going to show you today emanates from the work of the group. And we are very much motivated by the most challenging and urgent societal problems. A lot of the things I'm going to show you today tie back to important issues like climate change. We're also working on energy, planetary science challenges. And today I won't have time to show you all of the things we do. I'll take a few vignettes of what we do. And what we do is we specialize in this so-called complex systems modeling. That's where the name of the group comes from. And we look at problems through the glasses, if you will, of complex systems. And the way we solve this, how we go about it is that we do experiments. This is new from my time at Northwestern. When I was at Northwestern, I was purely a computational person. When we came to Caltech, thanks to a startup package, we were able to become an experimental group. And so we do quite a bit of experiments, and I'll show you some of those if we have time today. But the overall goal is always to predict the way that complex systems behave. And I won't belabor the point here. The motivation is very clear in many of these applications. One in particular has to do with CO2 emissions and the need to increase our population to about 10 billion by the year 2050. A fourth of the population used to live in cities like LA. Now that has been inverted. 3/4 of the world population live in places like LA. So you have these mega cities. And we believe that we need to increase or double our infrastructure by the year 2050. And we need to increase the amount of energy that we need to keep that growth by 200%. And at the same time, the CO2 levels have to drop to levels that are below the levels that we had in 1990. So for engineering, this is a huge, huge challenge, needing materials, needing new construction methods, needing a lot of know-how in order to meet the challenge of the day. And just to put in perspective, this is equivalent to building 8 New York cities per year until 2050 all over the world. That's a lot of cement and concrete. And you would like to replace that because, as you could probably see from the previous slide, cement and concrete, it's up here. It's one of the main producers of CO2 that, according to some of the numbers I have, it could account for up to 8% of what we produce. And so my group focuses on looking for alternative materials, using less materials, for instance, again, in the concept of building things. And you can see how this also applies to building things on Mars or on the moon, which is an area that we are interested in. So for the young in the room, this is really an opportunity. It's a golden age for engineering. I cannot think of another time when we had a bigger and most fundamental challenge for engineering, where civil engineering and mechanical engineering and aerospace will play a major role. And so the group today focuses on 4 main areas, if you will. Okay, so we are doing work on biology. This is new work that we started here at Caltech, rather, looking at how cells migrate and how they move. We also look at ants and how they dig tunnels, and how biological systems build environments. We have a big area in planetary science or space exploration. I won't talk too much about these 2 top areas today, but we work a lot on Mars, the moon. This is the new Viper rover that will go to the moon, and we're working on a new project that will look for water under the, this is the polar caps of the moon, and we're trying to sense water under the surface and then eventually extract it. Today, I'm going to focus on these 2 big areas here, materials and structures, and we're going to go back to geomaterials, which is the origin really of this group. But I'll show you that we're doing more than that. We're literally doing structures like domes and metamaterials for impact protection. And I'll touch upon a little bit on our work on climate, and in particular the modeling of sea ice. And so that's a plan. It's a little ambitious. It's going to be a little shallow by design, because I want to show you 3 little vignettes of the kind of things we're working on. And I would be remiss if I don't show you our work on particle breakage mechanics, because that's the work we're doing currently with Northwestern, with Giuseppe. I want to show you some of our data-driven multi-scale modeling work. This has, again, its origins at Northwestern, when we were there dreaming of multi-scale models. And finally, I'll show you something brand new that we're excited about on sea ice mechanics modeling. So with that, let us get started. So this is, again, unpublished work. This is ongoing work with John Harmon, my PhD student. That was CO, a graduate student at Northwestern, and you all know this guy. And we're very excited about this work. This is in the context of our MURI project. That's a multi-university or multidisciplinary university research initiative, and one of the collaborators is Northwestern. And the goal of that project is to look at the DNA, or the most important granular scale characteristics to describe particulate material in specifically sands and granular soils. And so some of you have seen some of these images. I just want to put everybody on the same page. We've been working since our time at Northwestern really on this level sets, discrete element methods that enable us to go from a tomographic image or a real array of particles and convert those particles into a digital twin, really, where each particle looks identical to the real thing. And so no more cutting corners using spherical particles. We can represent any particle with any shape, any morphology that you want. And through that, we're able to demonstrate, this is work that we've published before in JNPS, we've been able to show that we can really reproduce the behavior of granular materials to the point that we can predict things like shear bands, the timing of shear bands, the location of shear bands. And this is a comparison between experiment and model. You can see that even the amount of strain and rotation inside of shear bands is captured by the model. There's really no difference between the model and the computation. And so the model has been very successful at capturing the failure of these very complex systems, but this was all in the context of rigid particles. And so with Giuseppe and Dawa, we started to think of modeling breakage, because that's something that they're very interested in. They have these beautiful experiments, and we had been developing this technique also using level sets to split particles. So this image here just shows you the concept. Okay, there's a whole paper behind this. So if you have a level set that defines the shape of an original grain, that it's unbroken, you can think of a fracture, right, as another level set that goes through, or that could go through, the original level set. So phi2 can go through phi1 and literally split it according to your instructions, if you will. And then according to your instructions, then if you take the difference and the intersection of those level sets, you can literally end up with two now new particles, if you will. Okay, so that's the idea, and I hope these movies play. Yes, good. So here you see a grain that is being broken in the middle, and then on the very right over here, you see a bunch of grains that are being literally pulverized as a result of breakage. But we wanted to understand if given some instructions, if given some physics, these models could be any predictive. So you need to tell your model how you're going to split things. Now we're choosing to put the failure surface through the most the highest forces, but that's a modeling choice. You could choose whatever location and shape and pattern of fracture you would like to have. And then when that happens is given by some sort of breakage criterion, right? In the usual way where we are computing some average stress, sigma p, in the particle due to the forces that are acting in the particle. This forces F alpha at given locations X alpha. And then once you reach a certain strength, right, a certain failure criterion, then the particle breaks. And of course, we use things like Weibull distribution to differentiate for the different strength of the particles given their size and so on. Okay, so this is the model. How good is it? So in order to test how good it is, you have to compare it with experiments. And this is our collaboration with José and Dawa. So they have this beautiful tomographic images of particles that are real particles that are put in the so-called odometer test. That's essentially a one-dimensional test that is confined with a steel jacket, with a rigid jacket that is put into the X-ray machine, and they're able to see then, as a function of time, how these original particles that are whole break. And so here is a digital twin now of that experiment, that little sample that they stick into the X-ray machine. So we construct a grain-to-grain virtual sample, digital twin of the real sample, okay? So it looks identical to the real thing. The question is, does it behave identical to the real thing? So we impose the same boundary conditions with the instructions I talked to you about before, and then we show and we model the system and we observe how the system breaks, okay? So here is a plot generated by John Harmon of how the evolution of breakage happens in that sample. So you see the pink areas are grains that have undergone more than 5 breakage instances. And then my favorite plot in this is this one, where he's able to show how the forces, the interparticle forces, are evolving in time as the system breaks. And what's really interesting, and we're literally writing this paper with Giuseppe as we speak, is that these pockets where there is very high concentration of breakage, for example here, tend to have very low or relatively low density of forces. And that is because there you have lost the ability to carry forces. There's an area of high concentration of breakage, and therefore the forces need to redistribute to other zones, like for example over here and over here, where you have more pristine particles. This curve here seems trivial. This is your macroscopic stress strain curve. It's extremely difficult to get with continuum models, but here the model, the computational model, nails it literally and matches exactly the predictions of the experiment or the observations in the experiment. But this one here is a remarkable set of curves. This shows the evolution of the grain size distribution in the sample as a function of breakage. So you go from the orange curve, which is the original grain size distribution, towards the blue curve as a function of time, or as a function of breakage. And again, you cannot distinguish pretty much the line that is observed in the experiment and the line that is observed in the computational method. So the message here is that the method not only captures the macroscopic features of stress strain, but it's also able to capture the micromechanical features like grain size distribution. And on top of that, it's able to give you insight that no experiment can give you, which is access to the forces as a function of breakage. And with Giuseppe, we're very excited about the possibilities that opens then for more predictive continuum models in the future. These ones are more comparisons again. All I want to leave you with is, again, we're looking at different snapshots in time as the breakage progresses or as the macroscopic strain progresses. And you see that as things progress, grain scale features like sphericity evolve. So you start with a certain probability density function for your sphericity, and as a function of strain, you see that the sphericity shifts to the left. And you see that in the experiments, and you observe it also in the computational model. You see how things get lower, but also shift to the left. And this one here, comparing flatness and elongation, again, from the experiments and the model, they're one on top of the other. So I hope I'm able to, superficially, but very clearly convince you that the models and the experiments are really in, in tandem with each other, and the models give you insight that are really complementary to the experiments, and that this is really exciting for the possibility of having more predictive continuum models in the near future. So let me move on to the next vignette, which is this data-driven multi-scale model. This is work by my former student, Kostas Karapiperis. He's now at ETH Zurich, and this is a great collaboration with Michael Ortiz and Laurent Stenier from France. They developed really neat data-driven models for elasticity. And when Michael met my student Kostas, he was very excited about the possibility of doing multi-scale models for granular materials and for plasticity. And so what I'm going to show you is the beginning of that work, and we've continued that work to gradient plasticity, but I won't talk about gradient plasticity today. I'll just talk about the local plasticity framework that we've established with Michael and Stenia. So in classic mechanics, you have this set of governing equations, right? You have to satisfy the balance of linear momentum. That's equation 1. You have some perhaps equations like equation 2 that define your macroscopic strain. And then to close the problem, right, you typically have to introduce this constitutive relation, right, that tells you how your stress that appears in your balance of linear momentum equation evolves, say, as a function of the formation. Okay, and so this is a classical problem, and many of us work within this framework. Now, think of a different way of approaching any mechanics problem, where you define what's called a phase space, Z, that essentially that's a space that contains any possible pairs of stress and strain, okay, epsilon and sigma. Then think of an equilibrium set that contains the points in the phase space that satisfy your governing equations 1 and 2. Okay, so your balance of linear momentum and your definition of strength. Okay, notice that there is no mention of constitutive equation here. Then you have a material set that essentially is also a subset of Z. And here I like this graph because it really describes the problem. In this data-driven approach, you can think of the equilibrium set as a line or a plane in phase space. And then what you're looking for, your solution to your mechanics problem, to your boundary value problem, is the one that is the intersection of D with E. Okay, or at the very least, if there is no exact intersection, you're looking for that point D that comes from the data that satisfies your equilibrium set the closest. Okay, so you play this game of looking or searching for the closest D. In the continuum problem, in the classical problem, you find a unique solution, the unique intersection between E and D through the constitutive equation. So in the DD approach, then the whole idea becomes as follows. In granular materials, you have to face 2 major challenges. First, you have to face the idea that you have to deal with a history-dependent material. So there is an embedded notion of time, if you will. Um, so that as you go from, say, a previous set of E and D or a previous solution, you need to now find the next solution at, say, k plus 1. And that gives you two sub challenges, if you will. One is that you may not have data in the vicinity where you are now exploring. So you have an issue of phase space sampling. And two, you have a problem with characterizing, if you will, history. So what is an allowable, sense forward, if you will? What is allowed and what's disallowed in terms of history dependence for the material. So in terms of phase sampling, uh, our favorite solution right now relies on populating the phase space on the fly. So we have a powerful micromechanical model like LSDEM that we can call on demand anywhere, anytime, and we can then populate the stress strain phase space as we will, as we wish. Um, we also have, of course, experiments, and we use that data to constrain, the entire data set. But we rely, by and large, on the computational micromechanical model because it's just so easy and reliable to deploy and to populate anywhere, anytime. The more challenging part is how to do history dependence or history parameterization. And here, Costas developed two flavors. The main flavor is the thermodynamics flavor, where you essentially utilize another constraint. So you had the constraint of having to satisfy your, balance of linear momentum, your continuity equation. Now you're imposing a new constraint, which relies on the dissipation inequality, and enforce that your next stress, for example, sigma k plus 1, for a given epsilon at k plus 1, has to give you a dissipation inequality that is greater than 1, okay? That is greater than 0, that is positive, right? Accounting already for the free energy. So you can rely on this, and here's a schematic of how that looks like. Or the other flavor is a throwback to continuum modeling, to classical, constitutive modeling, which is to introduce an internal variable, say Q, that has certain rules that enable you to, to tell the material that things are moving in one direction or that you're going backwards. Say in the case of cyclic loading, right? Q keeps track of whether you were going in one direction of shear or you're unloading in the other direction. The beauty of Q, of the internal variable approach, is that it's very powerful if you understand the physics of your material. It's less general than the thermodynamics approach, and we have shown that both of them work very well for granular materials. We've done both. And the way you do both, either way, is to upscale from the grain scale information. So you have to construct, for the thermodynamics approach, you got to construct all of your parameters that go into the dissipation inequality, right? You have to compute all of those from the grain scale mechanics. And here we won't dwell on how you do this, but here's all of their definitions, and you can inspect them and see that everything is being built from the grain up. Okay, there's nothing relying on constitutive models or on phenomenology. It's all coming from the grain information. Same for the internal variable flavor. The one internal variable that we're very fond of is this one that is built on, again, our knowledge of granular materials being dependent on this anisotropies, right? So you can build in information about the structural anisotropy, how contacts, for example, are oriented, and this that we call the force anisotropies, how the forces are oriented in the sample. Again, you need to know your material in order to build these internal variables, and of course they need to be observable or obtainable from the grain scale information. Okay, and then you do the usual thing. You do a bunch of runs. You populate your phase space. Here we choose to do isotropic compression, simple shear, biaxial compression at different, with different conditions, so that we populate. Okay, you take the shotgun approach, and what you do then is, once you've obtained data, the colors here represent the data, and the black line with the diamond represents the results with DD. Okay, so constitutive free type simulations. Right here, we're doing a biaxial test, and then we compare that with running the biaxial test with a micromechanical model, and that's what we call validation with the black squares. All right, so there are a few things that I want to remark here, and these are two flavors of how we're doing it. The first remark I want to make is that you don't see much of a difference between the two flavors. They both seem to work. The other remark I want to make here is that you see that the biaxial test is sampling through different sets of data. So we're going from blue data all the way to red data and in between. Okay, so the DD approach is able to jump from one data set to another data set thanks to this history dependence approach. And the last remark I want to make is that the ground truth, if you will, the direct numerical simulation using the micromechanical approach, the level set approach, is on top of the data driven approach. Okay, there's really no difference. And you can then upscale this concept and do things like boundary value problems, where you free yourself from constitutive modeling. So we're going to run a triaxial experiment here shown with the LSDM, and we're going to do the same experiment with DD. I'm sorry, my computer is a little slow. And we're going to populate the DD by doing, again, by sampling that phase space with these little cubic cells, right? You need data again for DD, so that you can take from that data and choose how to go from A to B. So that's how this finite element model here is built. So it's sampling from material experiments, if you will, that are running on the side. They're not running in parallel. This run on the side, and then it's building a table, if you will, a database that the DD sample is reading from as it needs to. And these are the classic comparisons, right, that we make in mechanics. This is the stress strain curve. This is the dilatancy curve. And in the background, you see also the experimental curve, which we have from the experiments. And what's remarkable is that the DD model, so this one here in the center, has absolutely no information about the constitutive behavior. It's sampling everything it knows about stress and strain from this data that is being built on the side using very simple tests like shear tests. Of course, Zdenek is going to oppose this. He's going to say that this is mesh dependent, and he's right, because there is no length scale in this models here. It's all local plasticity, but we've extended this to gradient plasticity. So we have a length scale now that we can also obtain from the micromechanics, and we have a paper on that, but I won't talk about that in the interest of time. So let me quickly show you in the last 10 minutes or so our new work on sea ice mechanics. This is another collaboration with Andrew Thompson at Caltech and Dr. Devin O'Connor from Corel, the Coast Regions Research Engineering Laboratory of the Army. And the person driving this is Rigo Moncada, who's doing the modeling. So let me first give you a little bit of motivation. I think you all know this. We know that there is a feedback loop between global temperatures increasing and sea ice, and I'll show you some videos that will motivate that, and the mechanics, if you will, of sea ice loss contribute greatly to this cycle through things like albedo reduction and sea level rise that are also taken into account by global climate models that then predict further increases or decreases in global temperature. So it's all one part of a big loop. We're concentrating up here on the mechanics of sea ice and its loss and how that could contribute to these bigger climate questions. And we take the approach of, mechanics, ice being the mechanics problem. Again, some of you at Northwestern have studied this in the past. This is not a new mechanics area. Many people are interested in this. What we want to do is build a granular model of ice at the microscopic level, but also at the regional scale level. And I'm going to show you evidence of that at the regional scale. I won't show you evidence at the microscopic scale, but we're working on that as well. Let me show you some evidence at the regional scale. So here's the United States at the bottom, here's Canada, here's Greenland, and we're going to be focusing here on this area. And I hope you're able to hear the audio in this video. That is really the main motivation for this work.
So there's two main export regions for ice coming to the Arctic. So Fram Strait, which is on the between Greenland and Spitsbergen, is where most of the ice comes out of the Arctic. The stuff that comes out through Fram Strait is mostly first-year ice. It's kind of thinner ice. And then there's Nares Strait and the Canadian Arctic archipelago.
Okay, was the audio okay for that video? I'm going to show you, okay, good. I'm going to show you another one with similar audio. So same place.
Circulation of ice in the Arctic Ocean is driven by a massive current known as the Beaufort Gyre. The current has the effect of pushing the thickest, oldest ice to the northern shores of Canada and Greenland, near the entrance to the Nares Strait.
So Nares Strait is over, up against the kind of Canadian Arctic archipelago in northern Greenland. And that's where the oldest ice is in the Arctic, and also the thickest ice. And so the ice that comes through Nares Strait tends to be much thicker. This is the ice that is the oldest ice in the Arctic, and Nares Strait is the way that we can lose this ice.
Okay, so we're going to focus on the Nares Strait with this background. But before we do that, let me tell you the nuts and bolts of the model. Again, we're using level sets to simulate ice. And so we're going to have a way of describing the geometry of these ice flows that you saw in those videos, right? You see these big chunks of ice. So we're going to represent them in the same way we were representing grains before, same construct of a level set now for ice flows. Now, of course, here temperature is going to be important. So we have a way of solving for the heat equation, right? So we have a grid that is solving for temperature. And finally, we want to be able to do mechanics, right? So we perhaps this sea ice is breaking, it's splitting, it's growing. And so we want to be able to solve basic, say, linear elastic equations on our level sets. And then finally, through this whole ensemble, this whole construction, maybe split or reduce or expand our ice flows. Okay, so this is like the breakage problem I showed you before, with the addition that now you can increase or decrease the size of your ice because of melting and whatnot. And The other important difference now is that you have important coupling with the fluids, right? You don't have just grains in space. You are interacting with the ocean, with the water, but also with the wind. So there's significant coupling again between the solids and the fluids. In this model that I'm going to show you, there is only one-way coupling. The fluids influence the particles, but the particles do not influence the fluids. We are neglecting the influence of the particles in the fluids because we think that the ice flows are relatively small compared to the big currents. But you can build the whole, coupling if you want to. Here we're just taking a first approach. And as you saw there, an area of interest is Nares Strait, and I'm going to show you more pictures of Nares and Fram Strait. But the idea is that you take these images that you have from satellite pictures that give you idea of the composition of the ice flows, their location, their shapes, and so on. And then you can build computational models like this one on the left that tell you how these grains are interacting, how these ice flows are interacting, how they're melting, how they're breaking, etc. So the big idea is going to be using images again like before, but now to construct models of sea ice flow at the regional level. Okay, so let me skip this. This is more of the same. I'm going to skip this one too, because this just shows you that all I'm going to say about this is that these are different plots showing you the loss or the melting of ice as a function of shape. And you can see, as you would expect, that as you go from more circular ice flows to more elongated ice flows, of course, you lose mass faster. And so shape matters. That's all we're saying here with this slide. And so let's focus in the last couple minutes on the Nares Strait. So as you saw in those videos, it's a very important area. Lots of science being done right now, right there, because as you heard, this is believed to be the last bastion of Arctic ice. If there is going to be an area where ice will be lost last, if you will, that would be this Nares Strait. And the other reason why we're interested in this strait is that there is images, there is physical evidence that this area behaves very similarly to granular physics problems that we know and love. So this is one of my favorite images. This is that same Nares Strait. This is an image, this is not a model, and they're looking at how ice flows are breaking apart from the solid continuum and going into the strait. And in many cases, I can show you in another slide, they are clogging, they are bumping into each other, they're behaving very much like grains going through an hourglass type problem. So this inspired us to dream of models that are constructed. This is the same Nares Strait again. So this is a satellite image of it. Here are your ice flows. So we want to construct computer models that are based on those exact images at some snapshot in time. And then we want to impose the same boundary conditions, the same currents as we know are happening in the Nares Strait. And we want to be able to do things like this. We want to be able to observe the flow of the ice flows going through that Nares Straits and perhaps observe what satellite images have shown of jamming. So here we started with a geometry that was taken from satellite images, and we're imposing currents very much like those at the strait. And we are observing that the model predicts that at some point there is jamming here. If you account for for melting rather, right? So you're losing your mass due to melting, then of course you would expect that for the same, set of ice flows, you don't observe any jamming. Your system continues to flow, no problem. And then if you allow your sea ice to break, right? So here you see that beautiful breakage, very similar to the early part of a talk, you see that there's, again, no jamming, no clogging in the Nair Strait. And then, of course, you can account for the effect of currents. What happens if the flow changes angle just a tiny bit, right? What would that, how would that affect your physics? And this is my last slide. Again, this is just driving that same idea of the effect of a currents and how one produces one outcome and another current produces jamming, like you see here on the left side. So these are models at their infancy. They are still very much qualitative, but we believe they have a lot of promise. They can start from the real image, from the physical reality of the satellite images. They can account for all the boundary conditions, and they can even account for things like, I didn't show you here, growing of ice, refreezing. For example, they have seen that when you get clogging, you may, heal that area, if you will, so that this discontinuous ice becomes a new sheet of continuum ice over time. And if you put in the right physics, you can model all of that. Our goal is to eventually model the entire seasons of the Nair Strait, from the winter all the way to the summer, going from a continuum sheet of ice, break it apart, watch it flow, and then watch it refreeze and become a continuum again. But again, that's work in progress. Thank you very much for your attention. Let me close by just recapping these three vignettes. I showed you that in these complex systems, we can start by looking at physics-based models and using those physics-based models to predict things like breakage. And this is our beautiful work with Northwestern on particle breakage mechanics. And I showed you that the models are very predictive and they're able to give you insight that is just not available to you in experiments. Then I showed you some of our work on data-driven multiscale, where we completely do without any constitutive models, and our notion of stress and strain comes directly from the data and nothing but the data. And we are able to reproduce shear bands, their location, their strength, and so on, just using data-driven approaches. And we think that the future has a lot of promise for those models. And then finally, I showed you that you can take all of these ideas to a completely different setting, the regional scale, and dream of models that could be physics-based, as I showed you, but they could be data-based too. They could be data-driven in the future for, let's say, modeling sea ice mechanics and their evolution in time. And I think that the future will be all about physics-based models that can, capture reality without phenomenology, but also exploit the data. There's lots and lots of data being collected from experiments, from satellites, from rovers, from all kinds of probes. And there is no reason why this data should be living in parallel universes to the models. They should, at some point, all become one and the same. And I think that I've shown you that you can start to sort of blur the boundaries of where the experiment ended and where the computation starts. Where is the data? Where is the prediction? It's all one big continuum of approaches. With that, thank you so much for your attention. Visit our website if you are interested in our papers and our work, and I'll be happy to answer any questions you may have. Thank you.
Thank you so much, Jose. The cold nature of this medium doesn't allow us to really hear an applause, but I can see lots of virtual applauses going around, and I'm sure there are questions. And actually, I received a note by Gianluca.
I also have a couple of questions.
So Gianluca, Zdenek, and Horatio. Gianluca, you reserve your spot in advance.
Thank you, Jose. Very interesting presentation. You're doing fantastic work, of course. A comment and then a couple of questions. The comment is in some of your initial slides where you talk about climate change and CO2 and these type of things. And of course, you mentioned concrete, which seems to be the evil of this millennium, right? For CO2, you mentioned 8%. Some people say 11%, and these are all good numbers. The one thing I would comment on, however, is that it is a little bit simplistic just to look at production of CO2 due to the production of concrete. Really, that assessment must be done over the life cycle of any structure, any product, because you might have some embodied energy at the time of production, but then because of thermal property, you might save in heating and cooling over the next 100 years, right? And so if you use concrete versus wood, well, definitely you have more of those benefits, right? And so after 100 years, is that concrete more or less sustainable than wood? I don't know. It's not a clear answer. And so saying, wood is sustainable, and I'm all for wood structure. Don't take me, and I think we need to improve concrete, but just looking at production is a little bit simplistic in terms of just evaluating the impact of the climate and climate change. So that's the comment. Now, on the specific research, I have a question on your data-driven multi-scale approach. You mentioned several occasions that there is no constitutive equation in the approach. Isn't it true, though, that you do have a constitutive equation at one scale, which is your scale of the grains, right? For you might be just friction and contacts, and if you have a cemented stuff, it might be something else. But you do have a constitutive equation at that length scale, which then you upscale to generate your data sets that you use in the DD approach, right? So at some scale, you do have a constitutive equation. And you do need the constitutive equation, because you could argue that you could use experimental data, but those are never enough, right? Are never you never have enough experimental data to populate the space that you need to populate. So eventually you do need a computational framework with some constitutive equation, some length scale to actually get your pseudo experimental data.
Right.
Would you like to comment?
Yeah. So on the comment, I agree. I think that a lot of these numbers have to be taken with a grain of salt. The 8% is a way to put things in perspective. That's not saying, as you said, that in the long term, and when you look at all the data, concrete would come on top or below, right? These are just motivational numbers to sort of get us to think about alternatives. And in particular, as you know, you worked a lot on space. There is no cement in space, so there you have no alternative but to replace it, right? So that's with regards to the comment. With regards to the question, yes and no. I mean, you don't have to use a model, right? What I told you earlier is that in the data-driven approach, what you need is data. The data-driven approach is all about the data and nothing but the data. The next question is, where does the data come from? And the data, as you said, may come from experiments. So the day that experimentalists are able to produce all the data we need so that we no longer need models, then the data will come from experiments. I don't think that they will come. I think that the future, right, is a future where there are models at the lower scale, but they're not phenomenological models, right? They're basic physics models. When I say constitutive equation, I'm talking about the phenomenological sigma epsilon approach, right? That is pervasive. I'm talking about granular models that all they're doing is basic contact physics and mechanics that are all, they're all measurable. They're all, based on simple concepts that we can build up from. Yeah, those are models, but you could say that everything is a model, even the balance of linear momentum, it's a model, right? So
Exactly.
I'm not arguing for, escaping models. I'm arguing about, using phenomenological models.
Yeah.
And in fact, if I may interject, it's very related with this point, Jose. You use the virtual data to feed the data driven, right? And the idea is to have as a physics-based a model as possible. Going back to constitutive laws, yes, there are phenomenological laws, but you can envisage what if you had a constitutive law where you can put the fabric, where you can put the shape, where you can put the porosity and make it more feasible. That could be the source of virtual data. I mean, just to say, there is hope for concrete, but perhaps also for constitutive models.
No, if I can follow up just in 2 seconds, there is one case in which experimental data will never be available, which is the future, right? If you have to predict time-dependent phenomena, and we have many of those, especially long-term time-dependent phenomena, well, you cannot do 20 years of experiments. And even if you do, those are going to be the past 20 years, never the future 20 years. For those, you need predictions.
So Zdenek has a question, then Horatio, and
yes,
Alessia.
so congratulations, great lecture, great results. But I think some of your statements were too optimistic. For example, let me mention the question of digital twin. I recently lecture on from Stanford on aircraft twins. Now we design all engineering structures for failure probability 1 in a million. And the fact that it was demonstrated that in concrete structures, for example, large structures were failing with probability 1 in 1,000 led to a big change in the code. Side effect introduced. Now, 1 in a million to do either by simulations or experimentally, you need to simulate the structure 100 million times to do Monte Carlo. So I think in the foreseeable future, you will need a mathematical model for the material RVE to progress to that scale. And this is the reality. We, for example, have shown that you can have two materials which have, one is 8% stronger in the mean, but at the level of failure probability 1 in a million, it is 25% weaker. And this is generally neglected. Optimizing, well, then I have, of course, questions on the ice and other things, but I have a chance to talk to later. So, in the ice, I would like to mention a very important problem is that breakage of ice is thermal stresses from fluctuations of weather. Now, if in a cooling period you get thermal bending, and you propagate bending fractures, and the bending fracture tends to run through thick ice, not thin ice. And you can see propagation suddenly hundreds of kilometers of bending fracture in the Arctic Ocean. So these are things that somehow have to be included too. That's a big point in the breakage of ice. And of course, the buckling with shearing and all this, it's not just two-dimensional model.
Yeah, I agree, Zdenek. I agree on both counts. I think that the first point is well taken. So I wouldn't say that we're over optimistic. I would say that we have made the assumption, right? And this is again a modeling assumption that the world is deterministic, right? So everything I've shown you, assumes that the world is deterministic, right? If I know all the initial conditions, if I know all the interactions, I can predict the future, right? That's not always the case, as you very well pointed out. There is a very much stochastic nature to engineering and to nature, and people are working on those. You and others have worked on ways, right, of tying the deterministic approach with the stochastic approach. And I think that that's a very well taken point. As far as the the complexity of the sea ice mechanics, I 100% agree with you. There's a lot more complexity there. The good news is that the model is able to take all of that complexity if you need it. So the mechanics are there. You have a mesh. You can even do meshless mechanics, and you can add all of those features. But we are at our infancy at this point, and we didn't account for that yet. But you could if you wanted to.
So there is a explosion of questions. I want to satisfy all of them. So we have Horatio, Alessandro who wrote me, Gibril and Angie. We'll close it at that. Those who asked the question, please be short and sweet. Okay. So Horatio, you're next.
Yeah, Jose, I enjoyed your presentation very much. Nice to see you. And I have basically two questions. Should be much easier to answer than the previous ones. So the first question deals with what we are discussing now, the deterministic type of approach. In the level set, when you consider the fracture, do you need to take into account the roughness, which could be important in this particular media? And so how would you account for the length scales and the stochastic nature of the failure? Or maybe you didn't account that, but it's something that can be modeled in the future. And the second question deals with this data-driven type of approaches. Since, as you know, I am an experimentalist, I'm always curious, what did you learn from doing this that guides what type of experiments and how you sample the space, right? To get something that is accurate.
Those are great questions, Horacio. Thank you for being here. It's great to see you. So with regards to the first one, yes, we do account for friction and for contact. Because these models are expensive computationally, we usually build in the most basic rudimentary contact at first. So all we have here is your good old linear elastic constant contact, not even Hertzian, just linear elastic, and we have Coulomb friction with a constant coefficient of friction. As you know, I have colleagues here at Caltech that are very much interested in friction, people like Ares, Rosakis. He and I are collaborating on looking at the effect of rate-dependent friction, right? So what happens as you go from the static coefficient of friction to something more dynamic? What happens as you generate heat? My guess is that when you have what I call ephemeral contacts, so you just have touch and go, these effects are second order. But when you start to have more permanent contacts where you have two surfaces going against each other for a period of time, then these effects become very much significant. And so we're working on those things. And then your second question, which is fascinating, what we've learned, right, is two things. One is that someone said this earlier, experiments are beautiful, but they are limited in two ways. They are limited in the phase space sense. They give you literally points in a universe, so you will never be able to populate a large enough region with experiments in your lifetime or my lifetime. And then they are limited in their ability to predict the future, right? So I think that in the future, right, in the future of mechanics, what we're going to continue to see is experiments continuing to be the ground truth, the ultimate ground truth that models have to dial back to and show that they can reproduce in order to have any confidence that they can be used to populate the phase space in terms of data driven, right? If you cannot pass that test, that's the minimum test, then you cannot have any faith in your phase space, and then you're essentially writing fiction. You're not doing physics. So I think that that's our view of experiments, and I think that that's a very bright future for experiments and moving forward.
Thank you.
Thank you. Alessandro had a question.
Yes, I'll be quick. Thank you, Jose, again for the inspiring and rich presentation, and congratulations for this work. I have a quick comment about the ice analysis that you made about the ice mechanics that partly builds upon the previous comment of Zenek about the role of temperature, and your recent comment about the hydrodynamics of this problem, where we can have maybe particles of ice or blocks of ice that touch and go, or slower problems. So if understood correctly, in your models, you didn't account for any influence of temperature on the contact laws between these ice blocks. Now, I would expect that for fast movements, these might not play a significant role, because basically you're going to have this touch and go. But for slow flows, these might play a very dominant role in the whole problem, because not only the blocks will melt, but they will also interact differently. And so could you expand on that, on how, I'm very fascinated to understand how you could calibrate that, how you could get information on that, experimental or numerical, I don't know, but.
Yeah. That's a great point, and I agree with you. I think that that's what you said is absolutely true. Now, there are two ways in which you can account for that. One is that your level set, or the boundary of your ice flow is changing in time, and it could change as a function of temperature. We've done that, and we have the ability to do that. So the roughness, if you will, and the geometry of the object can change as a function of time and temperature and so on. Okay, and that's a dynamic feature that is evolving, and so that's available, and we've done it. The more profound feature is having contact mechanics that are a function of time, and this we haven't done, right? So you can, as you said very well, that depending on the temperature, depending on time, depending on many aspects of the physics, I can see, right, this contact mechanics changing and evolving. Now, the methods are able to do that. They need to be instructed how to do that, and that's the part that I don't know. I wouldn't know where to start, right, in writing an equation, right, that say changes the friction coefficient that's a function of